Hello everybody, let's discuss in this video the next step towards a transistor amplifier, namely how to use superposition when the transistor is a nonlinear element. How could superposition work in a nonlinear element, also known as small signal analysis? So let's draw a transistor. Draw a simple transistor as always. Yeah. Here it's much simpler than the transistors we usually draw. That's the transistor from one of the first videos. Let's do that one. And then here I think we've had it's the same as what we've had in one of the first videos, if you recall. And then here we had a 2-volt voltage source. Let's actually draw it not with a point source, but with a two-sided source. So let's do here, this is a 2-volt source. Here is the plus, here is the minus, and of course it continues from here and that was supposed to be a straight line, but this is a plus. Okay, and then great, okay, so we have this, and then above the collector we've had a 100 ohm resistor. Great, a 100 ohm resistor, and above that we've had a 10-volt voltage source. So I'm going to just draw it here. 10 minus. This is a 10-volt voltage source. That's what we've had, and it closes on here. Okay, and then the question is, at this point, so this is okay. We've analyzed this, and we found some results. But here is the new thing. What happens? 1 second. Okay, sorry. And then the question is, what happens if in addition to this voltage source, we have one more AC voltage source? So you can think of this one as a signal that we want to amplify. So we have like some AC source, maybe it's music or radio or something like that, or whatever it could be, and we want to amplify it. And the question is, how do we analyze it? So here we can see that the two sources have different frequencies. This one has some frequency above 0. Obviously that's an AC source, it has like frequency. This one is a DC source with a frequency of 0, so we cannot just add them up together. Normally, the way it's done is to use the principle of superposition. They hide this one, and in fact, well, you have to take one at a time, or actually you don't have to. Okay, to use the principle of superposition, you have to take, yes, you can either take one voltage source at a time, or you can take, for example, this one, the 2-volt source and the 10-volt source, analyze what happens with them present, then delete both and take the remaining one. So each one you have to take only once, but you can take two together. So we'll see that in a moment. And that's the principle of superposition. Here there is a problem with applying the principle of superposition because the transistor is a non-linear element, and the principle of superposition does not work on non-linear elements. Okay, and as a result, we would like to, for example, let's say we can take the 2-volt and 10-volt voltage source, analyze the currents and the voltages, and then take just the AC source. So yes, we can take those two sources at a time, see what happens, then remove them, put the AC source and AC source alone, and see what happens. And add up the currents, the voltages, and the sum will give you, and the sum of the currents and the voltages, if the principle of superposition worked, that would give you the currents and the voltages across the transistor. Here the principle of superposition does not work. And, well, okay. And then there are two things. If this AC signal is large, so that's probably like for example, well, maybe bigger than half a volt, even half a volt is kind of big, then I don't think there is any quick method to analyze it. What you would have to do in that case is analyze it per point of time. So for example, let's say that this was a very large signal that let's say that oscillated between -3 to +3 volts. In that case, there is no good way. If you want to know what happens across a transistor at a particular point of time, you would have to say 2 volts, and then here, let's say now it could be, it varies. Maybe we can take the maximum, and let's say that that's 3 volts, so that's at the maximum, minus 2k IB minus VBE, and then we have to figure out what VBE is, whether we have to figure out what VBE is. VBE could be, if it's bigger than 0.5, then it's in the transistor is either in the active or saturated state. If it's less than 0.5, then normally we say the transistor is in the cutoff state. So we saw that before. But in any case, and then we have that, and we solve that equation and analyze it. And if we want to know what happens, for example, when this oscillation is at, for example, at 1 volt, so there is no good way. You just do 2 plus 1 minus 2k IB minus VBE. That way we find IB, then we try to find IC, then we find VCE. So we can only find it one at a time. We cannot use superposition. We have to, and we cannot have a general formula to add these two signals. We have to just calculate the value for each point in time. This is for one point in time, this is for another point in time. But let's say the signal is small. Let's say the signal is something like -1/2 to 1/2, or something along those lines, maybe even smaller than that. Ideally, we're dealing with, this is actually pretty big, right? So ideally, we can deal with just a few millivolts, like maybe, well, that will be, for example, this is 10 millivolts. 100 of a volt is 10 millivolts. So if the signal is small, like those ones where the signal oscillates between small voltages, then we can still use superposition, but that is, calculate what happens when the small signal is not present, and then calculate what happens when the small signal is present. We can use superposition. But it has to be done in a slightly clever way. It cannot be done right off the bat. We have to do some work to get there. So what do we have to do to use the principle of superposition? First of all, I'm just going to erase that for now. First of all, we need to see where would the circuit be without the AC signal. So that's normal. That's like, where would the circuit be without the AC signal? So we do 2 volts minus 2k IB minus VBE. We assume that it's 0.7 and that the transistor is in the active state, and that assumption was actually borne out. Okay, and good, and we have that. And now we have to calculate IB. I'm going to go grab the calculator. 1 second. Okay, I found the calculator. So let's see what this comes out to be. So 1.3 divided by 2000. It's okay, 6.5 10 to the minus 4. Okay, so it's equals to 6.5 10 to the minus 4. And then IC, we remember what is 100 times IB, so it will be 6.5 10 to the minus 2. Oops, careful. Yeah. And then let's see what VCE comes out to. VCE comes out to be 10 minus 100 IC. So that's kind of useful. That's good. 10 to the minus 2. So it just comes out to be 3.5 volts. Or, well, this is not nice to do it like this. This was too much of a shortcut. Just okay. And then what is VCE? Well, then you do this minus VCE and then equals to 0. And then VCE, this completes the Kirchhoff law, and then VCE is 3.5 volts. We saw it in one of the first videos. So now this is the large signal values. We can call this large signal value is also known as the quiescent point. So we can say, no, that's not what I wanted. Is also known as the quiescent point. So we can say that IBQ, Q stands for the quiescent point, is 6.5 10 to the minus 4. ICQ, yeah, like there used to be an application with that name, is 6.5 10 to the minus 2. And VCE, Q stands for the quiescent point, is 3.5 volts. Okay, I'm going to erase how we got there. It's calculation we had done even at the very beginning of the study of the transistors. So we have that. So those are the large signal values. That's what we get when we have the large signal alone. Very well. Now, let's remove the large signals and analyze the circuit only with small signals. Okay, but to do that, we need to convert the transistor to a resistor. Now, the transistor is dynamic element. It's nothing like a resistor. But we can say that when a transistor is biased at this quiescent point, a transistor is IBQ, ICQ, VCQ, then for what the small signal will see, the small signal will approximately see VBE as a resistor. So the small signal, for the small signal, BE will appear almost as a particular resistor. Now, that is true only if that small signal stays pretty small. The larger the small signal, the less and less will this VBE seem like a resistor. But if the small signal stays pretty small, the VBE is actually like a resistor. Moreover, there is in the book, and now I have to open the book because I don't remember, there is a formula of how to compute. 1 second. Of how to compute it. It's actually a simple formula. I should have looked it up earlier. Okay. Before I actually started recording the video. That's me. Okay, let's find. Just 1 sec. I just need to find the formula. Okay, there we go. And the formula says that the value of this resistor, this is by the way called R pi or pi analysis or something, R pi analysis maybe. Maybe R pi analysis. The value of this resistor R pi is equal to beta Vt. Vt is actually simple. It's not a Thevenin equivalent, thank goodness. It's just a constant, more or less. And then ICQ. So beta for a typical transistor we saw is 100 most of the time. Vt is a kind of complicated constant from solid state physics, which I don't understand anything about, but I just note that at the room temperature it's usually 0.026, so you can use that as an approximate constant. ICQ we calculated to be 6.5 10 to the minus 2. So let's see what R pi comes down to. I have my calculator. 0.026 divided by 6.5 times 100. I got 40. Let's try one more time. So 100 times 100 times 0.026 divided by 6.5. Oh, it comes down, actually interesting, it comes down to 40. So it's a clean number. It's, I mean, rounded number. I didn't even have to round it. It really came out to be 40. Okay, so for the small signal actually sees 40 ohm resistor. Now slightly the difficult part now comes, unfortunately. Okay, so now we want to analyze the circuit with just based on what the small signal sees. Very well. And so on the principle of superposition, we can already consider the 2 volt and the 10 volt, so we don't erase them from the circuit and only leave the small signal. And we leave the transistor, but we approximate the transistor as a 40 ohm resistor. So this is a little, need to be careful here. Okay, let's try a nice color for that. Sorry. Okay, maybe bubblegum pink or something like that. Okay, so let's now, okay, we have, this is our AC signal, and along the way, it passes through 2 resistors, right? So along the way, when it goes, it would first pass through the 2K resistor and continues onwards. And then it passes through VBE, but we say that VBE is now, for a small signal, it's like a 40 ohm resistor. 2K, and this is 2K ohm, and this is 40 ohm. So that is what the small signal sees. And okay, so this is going to be tricky. This is what the small signal sees. Very well. And let's, now I want to change the color. So let's see. Yellow is okay. The small signal sees, so okay, there we go. And this is what it sees. So let's, well, obviously to compute it, we need to know the exact value, but let's say it oscillates from 0.01 to minus 0.01. So let's say currently at particular time, at some time, at some time, the voltage across the AC source is 0.01. Now it oscillates. It could be from plus 0.01 to minus 0.01. So it oscillates. But let's say at some point it's 0.01. So what do we see? We see that 0.01 minus 2k, let's call this I, minus 40, right? So this is just a very simple Kirchhoff law. I equals to 0. And what is this I? 0.01 divided by 2040, right? Okay, it's a very small number. It's 4.9 10 to the minus 6. 4.9 U. 4.9. And that's correct. It has to be smaller because the large signal, even the IB from the big source, is very, IB from the big source is 6.5 10 to the minus 4. So obviously from the small source, it has to be smaller than that. So this 4.9 10 to the minus 6. 10 to the minus 6. Okay, and if the voltage were, if the VAC were minus 0.01, then the current I would be obviously the other way around. So if it's minus 0.01, let's define the direction of the current like this. So if we define a priori that this is the direction of the current, then when the current goes the other direction, it will be 4.9 minus 4.9 10 to the minus 6. Very well. That is the current. So this is when AC is actually the negative, right? So this is at a positive. And now what is this current? Sorry. This current is the additional IB that the small signal contributes to the large signal. So what will be the value of IB, the final value? Well, we have final value of IB. Let's say IB final. We have IBQ, which is the large signal contribution, plus we have the I. Usually, I don't know how to designate it like this, but we can call it I small b. Well, of course, I small b varies. IBQ is fixed at 6.5 10 to the minus 4. Very well. And what is I small b? It varies, but we see that sometime when the voltage is 0.01, it's 4.9 10 to the minus 6. And we see that when the voltage is minus 0.01, it's minus 4, it's actually the negative of that. And it could be everything in between. When the small signal voltage is 0, then the small signal current is also 0. And then the final current is equal to the IBQ, right? When the small AC source is 0, then the small signal IB is also 0. And the final IB is 6.5 10 to the minus 4 plus 0 equals 6.5 10 to the minus 4. So we see that IB final goes between now we need to use a calculator. It goes between 6.5 10 to the minus 4 plus 4.9 10 to the minus 6. 6.5 10 to the minus, so this is like a very 6.549, right? So it's pretty small number. I don't like how I wrote it. So this goes between the max is 6.549 10 to the minus 4, and the min, calculator, no, and the min is 6.451. 6.451. That's about right. 6.4. That sounds right to me, right? 10 to the minus 4. So this is the range, right? So this is the range that the IB final takes. It goes between that value and that value. So you see, sometimes the small signal can be negative, but when it adds up to the big value, the final current is still positive. The final current still goes across BE. The current is not negative. But what is true, that the small signal can reduce the large signal. Like we see here, it reduces the large signal. But even after reducing the large signal, the final current still goes, the final current does not go backwards. The final current still goes like this. It's just that sometimes the small signal increases the current, sometimes it decreases, but it doesn't make the current reverse altogether. Very well. So this is IB final. Now, what would be the last thing for this video is what will be the final value of VBE. Now, usually we assume that VBE is 0.7, and that's okay. And that assumption still holds. But let's say we want to see how does the small signal affect VBE. We can ignore that effect and just say, oh, VBE is 0.7 because the transistor is still active. But let's say we want it to be very careful and see how the small signal affects VBE. Now remember that we replaced VBE with a resistor, the 40 ohm resistor. So the voltage across those 2 points is actually the effect of the small signal on VBE. So the voltage across the 40 ohm resistor, the voltage here, would be the effect of the small signal on VBE. So let's see what will be the final VBE. So the large signal VBE is, let's say large signal VBE is 0.7. It's not exactly but accurate, but so let's say that VBEQ is 0.7 volts. What will be the effect of the small signal of VBE? Well, you have to erase something. Okay, I'm going to erase this. Sorry, just erase it. Need to also erase the arrow, but it's okay. Oh, it's okay. And then what will be the effect of the small signal on VBE? So let's see. What is the maximum voltage across the 40 ohm resistor? Maybe like this one. What will be the what would be the maximum voltage across the 40 ohm resistor? Well, when the current is, the small signal current is 6.549 10 to the minus 4 times 40, that will be the VBE small, the maximum of the VBE small. So let's see what it comes down to. 6.549 10 to the minus 4. Oh, okay, I have to be very careful. Oh, sorry, no. Okay. So, no, it's not, it is a very small error, just I need to, no, I erased too much, okay, fine. It's, of course, we don't take the large signal, we take the small signal. So the small signal, even the 6 is wrong, the small signal is 4.9 10 to the minus 6. So VBE small max is 4.9. So this is the maximum IB current, 10 to the minus 6 times 40. So the current goes through a 40 ohm resistor. So 4.9 10 to the minus 6 times 40. 1.96 10 to the minus 4. It comes out to 1.96 10 to the minus 4. Okay. Volts. And the min VBE small min, well, that's when we have the negative voltage and the current goes the other way around. So we in fact have, right, the voltage goes the other way around, so we in fact have a voltage rise from the top to the bottom of the, we have a voltage rise from the top to the bottom of the 40 ohm resistor instead of having a voltage drop. So that would be 10 to the minus 6 times 40. So that's just the, with a minus sign, minus 1.96 10 to the minus 4. Okay, is that? I just want to see that I didn't make a calculation mistake. What is this? 4.9. Okay, looks correct. Okay, looks correct. Now, and again, the small signal does not live in a vacuum. That I think is a mistake, just to, the small signal combines with the big signal. So the final VBE is not just the big signal and it's not just the small signal. The final VBE is both, right? So the final VBE, VBE final is actually both, right? And what is the VBE final? Well, it's VBE from the large signal. That's a constant. We assume in our simple model that it's 0.7 volts. And now we have a plus minus 1.96 10 to the minus 4 volts. Now, we took the two most extreme cases. Sometimes the small signal is in fact 0, right? So it oscillates sometimes 0.1, sometimes 0.005, 0.002, and then anyway, it goes between 0.01 to negative 0.01, and it passes 0 in the middle. So when the small signal voltage is 0, the VBE final is just the same as the large signal VBE final. The small signal voltage is 0. It doesn't contribute anything, right? So if the small signal at a particular point of time was 0 volts, what would be the VBE in that case? Well, it's 0 volts. It's as though it doesn't exist. And then we are left with just the large signal voltage, which we approximated to be 0.7. Okay, oh, this took too long. Then, okay, so now we saw how the small signal affects IB and VBE. IB and, right, VBE. And now the next question will be, how does the small signal affect VCE and IC? But this video was already longer than I wanted to. So let's continue in the next video. Thank you, and we'll continue next time.